Okay, so I think we had really a very rich session today with a lot of different approaches that were presented for this hadronization and as well also for the Hydronic phase. So, of course, here the idea is to discuss whatever you feel like contributing to make progress in the field. And nevertheless, I have made some kind of a sketch line here of what we could discuss. And basically, I think the first thing that would be interesting might be to go through task 2, to which everyone has contributed, and I think there is still a chance to contribute in the upcoming days or weeks. And if you agree, then I will basically pass the various results here, and every model should feel free to comment on each plot. Okay, I don't have a specific comment for each line, obviously. We heard already from DAB which is the highest here. Why they could be the highest on this plot due to the specific ingredients. And if we look here, basically on what are the lowest curves here, this I don't know whether the model want to comment. It's a bit surprising because it seems is really the ratio that we have typically between the hadronization in AA and in PP, and something compatible to unity in the sense would mean here that there is no specific effect of hadronization in AA with respect to PP. So is it really what it means, or does the fact that these values here are rather low for those models is nothing but the fact that part of the C quarks are basically driven to lambda C, and this is why basically they get back here to unity. So I don't know whether Catania or Min, I don't know who is there for Catania. I'm sorry.
Paul.
Vincenzo will be there, right?
Yeah, I'm not
Yes,
sure
I'm
he's there.
here. I was disconnected, but now I connected
Vincenzo.
again.
Nice to have you back.
Thank you. So yeah, essentially here, I mean, what I can say is that when we were not including the lambda C, we were getting a peak. I hope Salvo can send, but he has in his talk, but he gets a peak quite similar to Tam and Duke, and then was going down back to 1 more quickly maybe than them. And so there was this large effect. Once you have to conserve the yield with lambda C, you go there. However, the effect is not negligible anyway, because you see it goes close to 1 at 4 GeV. So generally, anyway, he has a depletion at lower PT. So still is significant for our study at low PT.
Yeah, right, quite correct.
So did the non calculation change? Because before we were a bit puzzled as it went to 0.6, or was it a different plot?
No, sorry, I was confused as well. My mistake. I was confused as well by what we call HAA here. And I thought
was a poor choice.
So I've interacted with Xin without putting you all in CC because I don't want to disturb you. But now this is the real HAA as it should be. So it's still basic. Now it's going really close to unity here, but it's still large, basically here. Yes, please.
Yeah. It looks like there's a general feature for especially low momentum, and there is a suppression, and then there is an enhancement afterwards. So this is probably, oops.
I think it will be important to draw a baseline, which is purely just a fragmentation. And then, so that we can compare with all those HAA calculations, including various of different effects.
Yeah, okay, maybe I can comment on this, right? That there the dashed curve is the Llano curve, and I was wondering what to do, and I copied the Llano's curve. So you see the solid and the dashed are very similar. That's a joke. so you shouldn't read too much into, kind of the little wiggles on the dashed curve. Is just that the grid for energy loss is fairly widely spaced. It was meant to go to very high PT. So, this little dip around 7 GeV, kind of, you can forget about it. But the general feature of fragmentation, if you just want baseline from fragmentation, as you go to high PT, you see that it goes above 1. You can kind of see the remainder of those curves above 1. Like it's what, about 28, 30 GeV. And then the shape of the suppression is there is a minimum, and it depends on the calculation. In the Llano calculation, it's kind of between 10 and 5 GeV. And as I explained, you go through an inflection point. So in a sense, you're shifting the spectrum downwards. And so at high PT, there is suppression, but at low PT, at high PT, in this particular ratio, it looks like a small enhancement. And then when you go to low PT, it looks like a suppression, which you see. And, it's comparable to one at the inflection point of the RAA ratio. And this is the simple explanation of what the baseline will do without any coalescence.
Okay, so is there any other models that want to comment on the curves? Or...
I'm sorry, I was cut off somehow.
Yes, you were cut off. Yes, I don't know.
Yeah, my somehow I don't know what happened. Anyway, I was thinking that I was saying that there is separation at very low PT and followed by some enhancement. So this is probably because of the recombination of the coalescence that shift part of the low momentum to a little bit higher momentum. From quark to hadron, probably.
They gain energy.
What?
With the coalescence, the DV quark gain energy through the process.
Yeah. So that's what I'm saying. So this is but in general, the total number of charms is conserved, right? You have so it's shifted to a little bit high momentum. That's why you see suppression at low momentum and enhancement at high momentum.
No, it is not conserved in this channel. This is the point. I mean that.
What channel? I think if you include all, if you include all.
No, this is just no. It's just the D meson. It's just. Okay. I'm sorry. I mean there is a problem with this. That is just the D meson. It's the first plot of distance 2. Okay, and this what Vincenzo just explained.
That explains it. If you include all charmed meson, then they should be conserved, right?
Yeah, right.
Yeah.
Then there is a question on how to intercompare between.
Yeah.
How to compare between models that have this baryon production and those who do not. I mean, so this I don't know how we should proceed with this.
But one question, Paul. One question for Tamio, Ralph, or Minet. But in their approach, there is a change if you include lambda C or not, just to understand if it is any effect.
There will be a change.
How much it is, but
not a big change because there's a maybe I can say and Min can say. I think there's as it turns out, the inclusive production of lambda C doesn't change very much going from PP to AA, right? We have that ratio of 0.5 or 0.6 already in PP, as it should, because those are the experimental spectra, right? So the the inclusive yield of lambda C and D doesn't change all that much. There's a little bit of loss, I suppose, in the DS, but that's not that big. Maybe Min has more insight.
And that's for integrated yield, right? But here there's a PT dependence.
That's right. I just say about integrated yields, yes.
I think what's reflected here from this plot is comparing Tamu and Catania. Catania parts have a larger proportion of lambda C yield, so the dimension is much depleted compared to the Tamu. Yeah.
So you mean we have a larger effect because our lambda?
We have a larger lambda C to D.
Yeah, so that's right. I saw that on Salvo's figure. Your low PT lambda C over D ratio goes to about 0.8. So you have 30% larger ratio in AA on that one than we do, because our low PT goes to 0.5.
However, the good part is that before lambda C, that is the one more unknown, our approaches were much more similar indeed, as it should be. I mean, that is, now that there is the lambda C, okay, there is another, but when the lambda C will be fixed, in principle, the underlying the meson coalescence is very similar, I think. And then I think Berkeley, Tamu, Duke, they are all very similar. And instead, I think NAND gets more because of the small quark mass. This is my experience, but I don't know if Paul agrees.
No, this is what I've explained. So this is still, so this is still with this model that was presented at AMI. So in the meanwhile, yeah, I mean, we have corrected this, and I should put this curve on this plot as well. But nevertheless, we do not get down basically to this value. And one aspect that was advocated by Ralph is maybe because of our strong space momentum correlation, we have this extra boost. So the homework that I have to do is basically to take my model and then transform it in the momentum coalescence only and see whether it affects this product.
Yeah, that I think is a very good idea.
And what about QJet, if I may allowed, because here at this large PT, we are really the largest.
Maybe no representative here.
I don't think so. I don't know.
Peter Braun-Munzinger has his hand up.
Oh, I'm sorry, I cannot see the hand. So if someone can manage the hands up.
Okay, no problem.
I just wanted to say, of course, we compute lambda C to D also, but and we get between 0.5 and 0.6, as you have seen. But we cannot compare to data because Alice has not released the lambda C to D data, only in preliminary form. So you should keep that in mind. Okay.
Yeah, but Peter, your low PT goes back to around 0.2, which is the statistical model ratio, 0.25, something like this, right?
Very low PT, yes.
Yes. Right. So so the inclusive lambda C over D yield inherently in the statistical model is, of course, the statistical value with the PDG spectrum.
But that depends whether we use the enhanced lambda C's or not. Okay.
That's right. That's what I said. PDG spectrum.
Enhanced lambda C.
That's right. And then
so that will go up by quite a significant factor if we enhance, like for example you do. But we have to refrain from making any significant statements because as Alice members, you're not allowed to make any statements until the data are official. I just want to, so that you understand what our situation is. We cannot, for example, show a plot with data.
No, nobody, I don't think anybody was referring to data at this point.
Well, no, you did all the time, but.
Really? I referred to the PP data, which is 0.5.
Okay. Anyway, it's just so I think this is something which hopefully will be cleared up in the next few months.
Okay, so concrete question is for the purpose of comparison, because if we show this to the rest of the world and basically that we say that this ingredient has a major impact on the extraction of the transport coefficient, it makes basically a factor 2.5. So the question was whether for the purpose of comparing the things, it would be feasible for those models who have a lambda C simply to turn this channel off and make as if all C quarks were going to D-meson. Is it still possible, or would you consider this somehow as a kind of degradation of the model that is not acceptable due to your recent development?
But you cannot turn off lambda C altogether. That is clearly too much. You can leave it at an unboosted way. That is certainly possible.
Well, I think for Min, it would be no problem to, for example, simply work with the PDG values for the spectrum, and that would.
Yeah, that's what I meant. That's what I meant.
Yeah, so then you can turn it off in theoretical model. At least in some of the models, you can turn it off. In others, it is maybe not possible. But
yeah, I support that idea. Absolutely.
Okay. Good. So maybe we can move to the second.
Sorry, why not? Can I ask a question?
Sure.
Also a suggestion. Why, since there is this problem of the fact that the inclusion of lambda C can alter the normalization of the spectra, and why not considering another observable like the ratio of the average PT square of the distribution, which is something which should not be affected by the fact of including or not the lambda C?
I don't quite understand, Andrea, because this lambda C production depends on PT. So if you make the root.
Yeah, yes, okay, yes, but at least it could be a bit less affected. I mean.
Okay.
Probably.
Sorry, can I ask you? Paul?
Sure.
Yeah. I just want to be sure in this plot, because it stays like D-mesons. Is it really that in all models D star decays are accounted in this case?
Yes.
If some models have definitely excited states, if all decays are accounted, because we discussed lambda C, but what about other states?
Well, I think in the spirit of what asked, this is not the direct, those are the prompt. So in principle, if some models have the decays, the decays should be accounted for as well.
Yeah, okay.
That's the way I understood it. I don't know
Thanks.
whether it was for everyone, but.
Just for that mode, it was direct D0, not prompt.
So this we should be maybe more specific.
But by the way, just I saw mentioned that in our case, we took it as a real D-mesons. So without decays, which also might change the shape a little bit, I assume. But okay, just we should compare apples with apples. That's what's the origin.
Yes, then I think we would better go to the older HAA. In that case, we have no fit-on at all. I think everybody has no fit-on, just direct D-meson.
Yeah, I mean, we could take this is the old one, so it was for the purpose of comparison here. It was the old one, and indeed we should take this one and ask for the direct. Yes.
I think the old HAA may be better, and we should not call the new one HAA, call it G or something, or just leave it as the ratio of RAAs. Indeed.
Yeah, I left it as a ratio here. I think it is better.
Mm-hmm. And the old HAA is even cleaner.
It's not clear for me what is the advantage of this one over this one. I think this one was quite good for me. So if everybody agrees, maybe we can shift to the next issue. That is the one of the ratio of V2 of D-meson with respect to C quarks here. And there are a lot of course, lot of wiggles here that make the situation a bit difficult to read. But if you kind of smooth out those wiggles, it seems that there is some kind of group here, and there is a very strong, basically TAMU result. So, Ralph, can you explain this?
first, this is the final dimension V2, including also the hydronic phase contribution. And secondly, we have a lot of highly excited dimensional excited states. For those states, the spectrum, as a result of recombination, for those highly excited states, the spectrum becomes harder. That means the recombination component is pushed to higher PT. So finally, when you calculate the total V2, you do a weight. You do a weighted sum between the two components, collapse components and fermentation components, using the spectrum as the weight. That way.
Wait a second. I'm a bit lost because what you say is that the fact that you consider the decays should give you larger V2. I thought that usually the decays basically are kind of washing away these correlations.
No, I mean, if you include the highly excited states, then because they are more massive, then they are more they are more subject to the flow push. So that anyway, their spectrum from recombination becomes harder than the ground state dimension. And finally, this will harden the spectrum of the total dimension. And when we calculate the total V2, we do a weighted sum between the recombination components and the fermentation components with the spectrum as weights. But now the spectrum from recombination becomes harder due to the inclusion of the excited states. So this also contributes to a larger V2.
Yeah, no, I mean that the excited states are harder and have more V2s as the ground state is clear. But once you decay them to the ground state, it's not clear to me that the V2 is conserved. But anyhow, I think then we should be also more specific, and for those models who have indeed direct and prompt, maybe we should separate things.
So one thing that Min mentioned, which is that the hydronic phase effect is in there, right?
You're right.
Yes,
right.
I think that was not that was maybe a glitch, because I think we wanted to look at that at hadronization, right?
Right.
So you should, if that is true, you should, and everybody else did it at hadronization, then indeed there's the blue curve is not what it should be, and you should take out some 15% or so. That makes things look, of course, already a little different. 10–50%, so it'll go down some, but there's probably still a difference. So that needs to be corrected, Min. We need to really calculate the V2 for the dimensions at TC, not at T freeze out, and we should also maybe ask everybody to focus on the direct dimensions, not the feed down. Ignore the feed down. That would be cleaner, wouldn't it?
Ralph, I mean, so can I ask a question? Sure. Because you have a doubt. It remains above 2 also between 5 and 10 GeV. But in that region, there should be fragmentation that has a very low V2. Can it be that is only the coalescence part? Because if we consider the poor coalescence, we go up like Q, for example. It's just
okay. This is a good point. Yes, maybe I've got. I should check my calculation. This maybe just pure nation components.
Yeah, definitely. It's a total dimeson V2 at TC that should go in the numerator.
Yeah. Including fragmentation and coalescence, so the full hadronization.
Maybe this is just a recombination.
Okay, that needs to be straightened out. And for the time being, I think in all the other models, the feed down is probably included. Is it?
It has to be included because these are strong decays. There is nothing you can do.
Yeah, for comparison with data, it's clear. But for the purpose of model comparison, it might be cleaner to not do. But I just wanted to understand what the people in their model did, if they did include the feed down or not. And then you can make sure that, whatever the majority has done, it's fine. Unfortunately, we were not very clear about that.
But we showed Johanna showed that in the transverse momentum spectra, if you include the feed down properly, there is very little change.
That would be good.
It's a very strong compensation, which has to do with the same effect as what Min said, that the feed down from very heavy resonances, of course, remembers the flow from the heavy resonances, but on the other hand, the compensation is that the decay weakens it, and the two effects really essentially cancel, as Johanna showed.
Okay, that would be fine too.
And so the effect is really very, very small. You can look in her presentation. There is a plot which says thermal, purely thermal. That is actually the ground state only, no feed down.
Then I would advocate it would be good to have basically data for the direct and data for including the
data for direct doesn't exist. That is impossible.
Model data.
Model data.
You mean
Yeah,
okay.
Well, I'm a tourist, okay, so I mean model every time. Okay?
Not use the word data.
I use preliminary results every time. I'm a tourist, okay.
Okay, so should we then? I mean, I would hate to ask people to redo it if they've done it with the feed down, but you know, what Peter says, even if it's true at low PT, it might not. I'm not sure how it would work out at higher PT, right? Is that obvious?
No, this is why we need both. Okay.
No, but we have it as a function of PT. You can go and look.
Yeah, but you don't have the you have a corona effect, but that's relatively small.
Yes. No, it's not so small at high PT. You're right. That part, of course, is absolutely dominant at high PT for us.
Yes, but it's still smaller than the bulk production would be when you do a fragmentation of all the chunk of fiber.
We have not calculated something like that.
Right. So it is the corona part, and so probably much smaller in magnitude. I mean, one saw it from the comparison with the experimental data that this was smaller than what you would get if you actually describe the experimental data at higher PT.
So Peter, since we are probably 1,000 kilometers away, and I do not risk my life, I will ask a simple question. Have you ever considered to have the corona thickness to depend on the heavy quark mass to make it a bit larger for heavy quarks and for light ones?
No, I mean, certainly not. That is the only issue is whether there is corona, how you can define corona. And of course, the quark mass only goes into what actually is thermalized in the plasma. So if you make the heavy quark mass larger, then there will be probably less thermalized.
Exactly, and this is what we have. Is the rate of thermalization goes like 1 over the mass.
That would increase that increases, if you like, the contribution of corona.
Yes.
But our corona definition is essentially saying that in the fringes of the density distribution, it looks like PP, and there we don't care whether it's what the quark mass is. It is just defined by PP.
Okay. So, Andrea, since your model really belongs basically to a third class, and that I find quite elegant, I think it would be really fantastic to have a bit of data of Pauling on some of these curves. Do you think it would be possible for you?
Yeah, I will send you in these days. Okay, two figure I already shown for the HRIA, but also for the HV2, it's possible to produce them.
That would be really great. Okay, I don't know whether there's another specific comment on this plot. Maybe we can go to the next one if everybody agrees. That was basically also what we have from the EMI report, comparing really genuinely two different approaches, and there we saw that the difference between two generic classes of model is in the end not that large, basically, for the V2, which might be encouraging. And then we have a plot, typically same plot for the lambda C, both the ratio of ARA and the V2. So we have, of course, much less contenders here. So I don't know whether some of you want to comment the difference, and especially the difference here in the peak. Okay, it seems really that comparing Catania and Tamu, there is a factor 2 in the PT. Is this well understood?
And do you remember whether this curves also focus on the coalescence, or does it have both the coalescence and the fragmentation component in it?
Both.
Both. Okay, great. Thanks.
Okay, so I withdraw my question. And what about the difference between LBT and the other two? Is there still any representative of LBT with us? Vaccinian, you're there, so.
Yeah.
How high does it go, by the way? Xin Dong,
This is for just lambda?
That's lambda C, yes. That's solely
Okay.
lambda C.
I don't know whether Xin, you have the latest. Do you have the latest results from Shanshan? I have no idea, actually.
Okay.
But it's a bit strange. Maybe there is something I miss, because more or less the lambda C over D peak is similar in this approach, more or less. I mean, there is not a vector 2 difference. So I can understand the PT, it can be shifted or larger, but the peak is so different. It's strange. Maybe it's plotted something different, because more or less the quark distributions around 2-3 GeV are not so different, I think, among us, right?
But there's one critical difference, and these are really the space momentum correlations, right? Which extends the reach of the coalescence quite significantly for the lambda C, because you have two light quarks in there. But of course,
this is mainly a difference between us, right?
Right, between blue and.
I agree. But we have a kind of space momentum correlation, but probably are quite weaker. The shift in PT, I understand, but you see our peak is comparable. I refer more to LBT that is much higher. Maybe what is plot, because at the end they have a lambda C over D that is not so different with respect to.
Another thing is we do have many more highly excited baryons, much more massive baryons. Their spectrum is significantly harder than the ground state. That also puts this ratio out.
The heavy baryons, that really makes a difference. Yeah, but I think Enzo was talking about orange versus gray, right?
Yeah, right.
In the magnitude.
So probably we should check with Shanshan that really he has plotted the expected quantity. Would be interesting to understand, because indeed, as Vincenzo says, in the end, if you look at the final predictions, they do not look quite different between LBT and the other two approaches. Okay, so maybe this we can skip. Then there is a role of the Ironical Phase, which seems rather mild. If you look here at the ARA, which is historically known to be built rather early in the course of the evolution. I also took the freedom here to put a band basically where this preliminary hypothesis would be. So I don't know whether there should have much discussion on this specific observable.
I remember you're using this essential coefficients, right?
Sorry?
You're using Hydronic transport coefficients or cross sections which are from this Ovtchenchuk calculation, right?
No, this was with Ovtchenchuk was at the time where basically we had no afterburner, so nothing was connected. And then what we did recently was to assemble this EPOS and then our heavy quark transport and then this ULQMD. So this really this effect from the medium is a genuine implementation of ULQMD. It was kind of a cross-section implemented by Jan Steinheimer in the ULQMD.
Yeah, this is pretty noticeable, right? 25% is pretty noticeable.
Well, there is a large error. As I say, it's still preliminary, but
okay.
But Paul, maybe it's precisely related to the strength of the cross sections which you implemented, and also on duration of your hadronic phase. All depends when you start to do your particularization. What criteria do you use to start particularization in your hydrocalculations?
We use a freeze-out temperature of 155.
Okay.
Which is pretty low. I mean, let's not focus on this. But I took the freedom to add this because this afterburner is ULQMD, and I could not find any prediction of. I don't know. I mean, Stefan told us they're also using ULQMD or now SMASH. And so probably, I mean, they should add some plot for their model as well. But the purpose of here was not to show that I have a discrepancy, but more that the difference with respect to the other two is kind of much smaller than with respect to this kind of discrepancy here. So my viewpoint is that we should work really to understand mostly this in the first place and maybe let this for a second time. I mean, that was more my idea here.
Sure. And the V2 is probably a little bigger. Yeah, okay.
Yeah, and of course.
Not really. Not really.
Well, at low PT, I mean, we have here commonly between PhD and TEM, you both find here a strong effect on the V2. I don't know whether you want to comment on this.
Yeah, that's a flow effect which pushes out, you know, the V2. If it's strong enough, if the flow is strong enough, the V2 can become negative. So this is what's happening. So even a relatively small flow effect can push out a lot of particles at low PT. And in plane, of course, in plane, the flow is larger, so it gets pushed out. I found it actually quite encouraging that that this microscopic transport and the hydro run all the way down to thermal freeze-out are not all that different.
Yeah, because the way you implement it is that you run your hydro down to the chemical freeze-out, correct?
Thermal freeze-out.
Thermal freeze-out. Yeah, sure.
That's right.
Yeah. That's also the approach we had with Ovtchenchuk.
Yeah, it's also interesting that I thought there somehow the coalescence will increase the V2 significantly somehow. At least for the TexSM model, it seems does not really have that kind of effect.
No, this is not coalescence. This is just the effect of the hadronic evolution after.
That was seen. This was the coalescence. Now we are here on the hadronic evolution.
This is only a hadronic.
And hadronic rescattering really plays a role. That's what ISO has shown today, at least in our case. So at least up to 20% or 30% level, or even more depending on the beam. So it cannot be neglected.
Is there other comments on this task 2? So if not, I think it would be good then to make a second round. Probably it would be even more motivating if we foresee some kind of common small publication, but this of course we need to discuss all together at the end of this week. And then basically coming back to some of the points here that I have identified, I find myself that making those comparisons, at least up to a certain point, that are quite interesting. I guess that for the hadronization, it's just the first round that we make. Although we had already something in the EMI report, still a lot of things to do. And then there would be two ways, basically, to make step further. The first one would be really to start from something that is maybe a bit too much ambitious. That would be to start from a similar hydro for everyone and from the same T spectrum at the time of the freeze out, and then each of the model would implement its hadronization. This might be, of course, a bit ambitious and maybe even more ambitious, but this would be kind of attacking the problem from the other side, would be to be able to resort to a common hadronization package and see the effect it does on the various models. I don't know how much, or maybe there are other ideas for the things that we could do in common. But
I think using use the same kind of common hydro will be the first step. Very important step.
Yeah, but we also need that is okay. The first step, and then we also need basically to start from the same C quark or B quark spectrum. Otherwise,
that is not very controversial, right? We just use some kind of the state of the art PQCD spectrum.
But Paul, concerning the common hydro, but that's what Shanshan developed somehow, and that's what we did in some sense.
Yeah. You mean in this recent work?
Yes, of course. Yes. Which Hinyan and all of us did. So these exercises, I think, has been done already, or not?
Not really.
No.
But it was not done common hadronization. Okay.
No. Yeah. The question of hadronization was left to different models.
In the last report, we only look at the brick problem. We did not have a common hydro. No.
I think we all have in mind different reports. Okay, so
Paul, I mean also the study which we did together with the DUE group, and where you also have been involved, and then we use the same hydro for different transport coefficients. Maybe we can use this hydro because it's developed already.
That's true, but
Stefan Bass.
That's true. I know, but I'm not sure. I'm not, for different transport coefficient, Elena. But now what I say is that one thing we could do is that we use all same hydro, same C quark spectrum at the end of the evolution. Of course, there is a question of the mass and those kind of things. And then each of the model applies a specific hadronization scheme. Okay, and then we see what we get.
Well, I'm sorry, but for us, it's absolutely impossible. As you know, we are a microscopic model. We can only provide transport coefficients for hydro and do in this way, but how we can do hadronization or something else?
No. I mean, what I've seen from TESO was more something like a standard coalescence procedure.
Yeah, sure. That's true. But how I can replace my dynamic by hydro? We can do that, of course, in terms of transport coefficients, and that's what we did in some sense.
Elena, the question is, you stop the evolution at the end of the QGP phase, okay, or whatever you call it, okay? And then let's assume we all have a common hydro with a common C spectrum, and then we just plug our respective hadronization procedure. And I think for all models relying on coalescence, that would be rather easy task to do. Now for model relying on a resonance model, which maybe dive a bit deeper into the QGP, this might be more difficult.
Paul, I understand. I think your proposed schedule is very nice. On the other hand, I think we probably just take one step at a time. And for example, maybe we can just do the same, your item A first, like same hydro, same C spectrum, and look at the final like C quark distribution spectrum first.
Sure.
And then go on after we finish this comparison, and then we go on to the B.
Yes, Tinian,
Yeah,
I was just discussing the A.
I do not really understand, because we have done most of this already. I mean, in the paper of Yingru, in Stefan Bass group, where all you participated, I mean, we had separated the initial condition, we had separated the expansion, we had separated all these parts, which we can do modular. So we can switch off one or the other time evolution, one or the other initial condition. The only thing what we didn't do is the hadronization.
Exactly.
And I think that's the natural
Can somebody give a report about this Duke report, because I'm not really aware of that.
Yeah, I was talking about this in my talk, but I can send it to you. I mean, it's not a problem. But in this respect, the things was missed because we didn't have the time. It's just hadronization.
And we are precisely in a session that I'm convening about hadronization.
That is completely clear. But I think the rest, because we are talking now to get different initial conditions and things like this, I think this is done.
Not at all.
What we need is get this hadronization procedure of the different programs now in a ways, and we can attach it to this common time evolution what we have before.
That's exactly what I'm suggesting, that we should use a common hydro.
I do not contradict you. It was just that it was in the meantime sounding as much more complicated than it is actually, because the first part is done. And now comes the second part, which has to be done. And
somebody send a link to this.
Yes, I sent it. It's not a problem.
Yeah, please. You can do it email or on the chat here, because not everybody are aware of this.
I have just to look it up, but it's not a problem. You find it in my talk as well, but I do it. Look it up.
Okay, so basically. We should discuss, of course, with the various models, whether we would like basically to accomplish this task, okay, in a reasonable future. Then there was this point about concrete consequences of the violation of conservation laws. I mean, basically, I must confess that even if I'm author of this report, I never fully understood here this comparison between the resonance reaction resonance mechanism in TAMU and this usual coalescence. So it seems that basically here there is for 300 MeV. So precisely, this is what I'm sorry. I mean, it's exactly the work that was done, okay, already for two models. It was the one of TAMU here, and basically this coalescence that has been developed much further by a Catania group. But it seems really that when you take different masses, okay, then the difference are huge, is it still basically status that survives, or is there some kind of evolution with respect to this? And how do we face this problem? Basically, I'm sorry, it's maybe more generic questions, but if someone wants to react about this.
So I can say a few things. So first of all, there's a trivial mass dependence and a non-trivial mass dependence, right? The trivial is that if you have heavier quarks, they're just less around, and so you reduce the coalescence. The more non-trivial aspect of that is the velocity match or mismatch. That's one thing, you know. And qualitatively, it has the same features, but quantitatively, of course, quite different. The other, yeah.
Please. No, of course. While the red is above the green, is above the blue, is clear to me. But why there is so kind of inversion? Okay, why is there so large difference specifically for these two values between the two approaches? There's still a mystery. Okay.
Okay. So I will. Yeah. Okay.
But I think you mean.
But there's one other thing. Can I just finish? What my observation was. Sorry, Enzo. The other thing is you see that the resonance recognition is actually significantly softer, right? And I believe that this really has to do with the equilibrium limit, right? That the ORM pushes you towards the equilibrium limit, and that means that if you do coalescence at high PT, you're actually reducing the RAA. And that is different from collinear, where you're always pushing up.
Mm-hmm.
If it's the only lesson I go from this calculation.
Can I?
Please.
Yeah. No, I mean, the comparison shows that when the mass is around 300 MeV, I don't know which one is the charm mass, you get very close. Of course, also with the yield. Of course, when you go in the tail, you start to see a difference. However, this is a calculation not really in a box in equilibrium. If I remember, was just an heavy ion collision in which you take the diffusion coefficient that is 5 times larger than the one in PQCD. So in the tail, you get some non-equilibrium in principle that can be different depending if you do collinear, if you do a wave function, or which kind of wave function you have, which may be in itself reasonable. So I think it would be better to do what the LBT has done to make really a comparison. However, in the tail, where in the real case, in the tail where you have non-equilibrium and you have also part of fragmentation, maybe the difference is not that large. I mean, I think
no, but the question was here about conservation laws, and I have to insist on that. That there is a principal difference here, that the collinear will always tend to increase the momentum of the D meson relative to the charm quark, and if you and that is violating the second law of thermodynamics, right? It's clear. You focus on, even in principle, you focus on a very specific configuration, and you don't allow for all the possibilities.
But you are using here.
You don't account for all the different possibilities that you can form a D meson from non-collinear, and that's in a way the entropy, or also the you can form a D meson and slow it down, right? That's absolutely possible. If you have a head-on collision between a light quark and a D meson, you slow it down, right? And
I agree.
Yeah,
I agree, but we don't have a collinear coalescence, right?
That's what I'm saying, and that's a reason, in my opinion. I believe that this is the reason of the different slopes that one can take away from this.
But you are already on. Please go ahead. Yes.
No, just I think we agree. I mean, it would be better to do the comparison just in the box, and maybe the coalescence you have used here gets an effect that is a bit larger with respect to the more realistic coalescence. This is, I mean, I suspect that unless you go maybe at very large PT, the difference is not so large if you don't have collinear coalescence, and then in the realistic model you have also fragmentation and so on. So maybe we can do more quantitative, but the starting point seems not so. This is
why are you speaking? This calculation, if I'm not mistaken, I thought was done with equilibrium distributions. Was basically equilibrium.
If I remember, no, you see, it's an heavy ion collision. I think it's just with strong gamma taken from PQCD, but of course, if you do that in the tail, you are not exactly in equilibrium.
I'm really lost. I'm sorry. I mean, this is basically what was supposed to be. That's basically. I thought this would be basically this light quark spectrum equilibrium that was convoluted with this heavy quark spectrum, with basically your both approaches.
So I just looked it up in the so we did take the 5 times PQCD Langevin, we convoluted it with thermal light quark spectra, right?
Yes, this exactly. But there is nothing like heavy ion.
Well, the Langevin or the charm quark.
No, it's the Langevin for the charm quark. You see, it's lead 2.67 TeV. I mean, it's already a good indication. I think in the box can be better. But
my naive question is, why do we have here a factor 10 between two approaches when you take mass 0 and as well a factor 10 when you take here 500 MeV? But maybe I'm too stupid there. understand.
Well, look, Paul, maybe I can answer a little bit. So if you look at the upper right, you see that the like core content changes by, you know, factor 10 or so, even less, right? Mm-hmm. But in the calculation, the D-meson content changes much more dramatically, right?
Yes.
So this is an effect of the coalescence somehow, right?
Okay.
And so the gradient, I don't see that. Yeah, the gradient is quite different. Well, actually, not that different. I don't know. Is it?
I don't know, but there is the DND dy. It's a mistake that is a factor 10 smaller in the case of 500 MeV. Maybe it's the 500 MeV coalescence. I read 0.053 and the other 0.0046 maybe.
Yeah, that's a big difference. Yeah. Oh yeah. I agree. There's something to be understood for sure that we haven't digested.
But okay, I mean that's probably room for a smaller group of people, and including a naive person like myself. Now, another point that I wanted to raise is it might be good at some point that we basically have a more detailed discussion about the ingredients, at least in all approaches that are making coalescence, and try maybe in the first place to collect the various parameters that are used, okay, and try to make a map between those models who allow themselves to have overall normalization, and which degeneracy factor do the model takes. And I think to have something like a collection of detailed parameters might help a little bit in building some collective view. Now, I'm not sure how we make progress after. Maybe one step. I don't know whether there are some comments in this.
Yeah, I'm 100% sharing that concern. I mean, we can elaborate on all the differences, which is sort of the stage we are doing, right? But then what? How do we reduce the bunch of curves or the bunch of models that we have, right? This is the goal, right? And at some point we either do it or we don't. But that's precisely my concern. You know, we can keep doing comparisons but we have to take, in principle, if you really want to make them work, or benefit from it, we should, we will probably have to make some decisions of what is more reasonable than other, right?
Yeah. I don't see much as a possibilities in just going ahead and take a common initial condition or even a common hydro freeze-out condition, and then do the different kinds of coalescence and fragmentation models.
No, here I'm really speaking about detailed ingredients for the coalescence and the hadronization.
But I mean, that you see then when you have a common initial condition. I mean, if you have already an input which is different, then I think it's quite difficult to separate now what the different models do to this. But I mean, if you have a common freeze-out conditions, that means the positions of the partons at the end before the hadronize, then each model can take this distribution, and then we can see what the differences make.
But I think it has nothing to do with the initial conditions. Okay, for instance, some of the model we really strictly assume, okay, that only one pair out of 9 will go. I mean, through the coalescence, because they're kind of singlets. Okay, while I think other models simply do not implement this kind of constraint, they just make arbitrary renormalization, and then they kind of advocate, okay, there is some kind of God-given dynamical principle that is such that a heavy quark, that a heavy light will coalesce at 0 pt. These are really two different approaches. Okay, and at some point we need probably to have some discussion and to nail down what seems more reasonable than the other.
Yes, that is completely true, Paul. But the problem is one has to separate, I think, two things. The one thing, what does really a specific model do for a given initial condition, with initial condition of the Ironic collision. The initial condition, I mean, at the point when we heteronize the system. And this is done differently in different models, different temperatures, all these kinds are different. But in order to study really the consequences of coalescence and fragmentation, we have to start, I think, from a common starting point. That means the partons at freeze out. And then we can look what the different models give as a final V2 or as a final RAA for the coalescence. And then comes
And that was exactly this baby step which we did in this figure, right?
Exactly. So, by the way, Paul, I think it's absolutely right. You can compare the consequences of hadronization only if you start exactly with the same things, because otherwise, how can you trace what is the origin of the differences? So you should start with the same initial condition, with the same amount of charm quarks and so on. So we should do similar things what we did in our common study. And actually, I sent the last references, the right one to this what York addressed, and in the chat, I mean, and the previous one, it was for Shanshan study for those who did not participate in that, to be informed.
Okay,
But this is start with the same things.
This is precisely what the reason why this was the very first point that I mentioned here. Okay, that we should have a kind of a common tool.
But I just want to say that it's something developed already, and one can use it for further study. It's available, and the same initial conditions and so on, which is important is also. So we can profit from that it's already was realized, and go further.
Is it still maintained?
Yeah, sure. I think it was a Hydro and a Stefan Bass group, and the two types of initial conditions. One, it was, I think, Trento initial conditions. Yes, another, we provided with PHSD, such that we also can compare to our models, and the same Hydro. Yeah.
Perfect.
Yeah.
Then I think it's in parallel, some little group of researchers can really scan through all models which are interested in participating in this initiative and collect nevertheless the ingredients so that we are ready for the comparison.
I mean, in this model we had tested, I mean, you have been co-author, we have tested the transport coefficients of all the models which were available. They have calculated the drift and diffusion coefficients, and so we can just move from one to the other.
It is the third time that you remind me I'm co-author of this paper. It is becoming a bit annoying for me, because this kind of gives a picture. I don't even know the papers at which I contributed.
Sorry, said I didn't want to do.
But as I told you, here my task is not to discuss the transport coefficient. I am perfectly aware we did this. But basically, what I wanted to insist is that we should precisely use this kind of works that's already been done now to make the intercomparison of hadronization. Okay,
could not more agree, Paul.
Thank you, Jörg. Thank you. Okay, and then there is, I think for me, the $1 million bucks question is how we make deeper routing with a theory, and especially now that we are seeing some kind of a spectrum of models. Okay, that LBT in the end is something like 2 + 1 gives 2, because there are pions that is radiating. So there is some kind of mix between this resonance model and the coalescence. And I don't know whether someone want to comment on this. I mean, Henrik also had some thought about having maybe a transport theory that would be better adapted near TC. I don't know whether someone has planned to develop something and would like to share his thought with us today.
Hendrik seems to be
away.
Away from the.
No, I'm still here, but I haven't anything new yet.
The thing, at least, that I can share myself, but it is not D-meson, but it is Quarkonia. That recently what we have done, because there's a lot of work on Quarkonia as well, as you know, what we have done, for instance, was to implement some kind of, let's call it stochastic Schrödinger equation, or Lindblad equations, some kind of framework where you are able to describe both friction and also interaction of the two heavy quarks with the medium, and then we fed this in a cooling medium to see what leads to this hadronization. And at least there is one lesson that we got from it, is everything but instantaneous. That once you are facing a heavy system, you need a long time in order to bind things. I mean, it's a really long story.
Okay, and are you in the right equilibrium limit at the end?
No, in the end.
This would be progress. In this Lindblad, you always have this trouble, right?
No, it is, what I'm speaking about is the formalisms that have been developed by Roland and myself. And the first thing that we have checked, indeed, that is if you start from any kind of state at a fixed temperature, at the end, you reach really the Boltzmann weight. So,
that's great,
yeah. And so we have kind of, right, I mean, we have benchmarked this, and then you can consider the question of evolving temperature. And it takes time. I mean,
yeah, sure. That's a tough thing, yeah.
I agree that.
Please, Ralph. Yes.
I agree that I would also like to understand better in how far the various coalescence or recombination models that are being used, or how do they compare to the equilibrium limit that, say, the statistical harmonization model has, right? From what I see, I think there can be a rather large variations. And what frankly speaking, bothers me a little bit is that the equilibrium limit is, or the chemistry is controlled by parameters which really don't have to do much with thermal equilibrium, right? If you control your equilibrium limit by, say, a radius parameter, I don't see really the connection to thermal equilibrium there, right? Or chemical equilibrium, I should say.
Yeah, but also, I mean, your RRM is a kinetic model, right? So this has all these features.
Yeah, I'm not here to advocate my model. So
yeah, but then I
understand. I appreciate your support, Hendrik. But I would like to understand how the existing coalescence model, including everything, how they control the chemistry, because chemistry is also an important observable that is now pushed very much by the experimentalists, and we should really understand whether we can make robust and reliable predictions about the chemistry. And
yes,
to do that, we should understand what controls the chemistry in a given model, right? And at the end of the day, in the equilibrium limit, it should be only controlled by the masses of the states, right? And that's general.
The mass action law, or SAHA, or how you want to call it.
But then I see models where the chemistry is controlled by things like a radius parameter, right? And that's, frankly speaking, what bothers me.
That's the problem with coalescence, right?
Yes, but Ralph, in general, it's not said that you get all the particles in equilibrium, right? It can be not. If a model does not recover the equilibrium limit, also the data will show that that is wrong, right? If at some point we get the lambda C over D is close to the statistical hadronization model for P that is low, then that model is just wrong, right? But in principle, it's not said that is so.
I think that the goal must be that in a box calculation you get the right equilibrium, right?
No, Hendrik. This
then you use the transport model or whatever fancy quantum model to do the off equilibrium. But if the equilibrium limit is uncontrolled, I don't know whether to believe anything, right?
But the chemical, but of course we don't have that, right? Because the coalescence is an instantaneous model in which you do the overlap more or less of the wave function. So you don't have all the dynamics that brings you to equilibrium.
Yes, sure. That's the problem, right?
Well, but it's been a model useful to predict several futures that you see in avian collisions. It's not, of course, if you have everything, you can do that, but doesn't mean.
You see, I can see that the coalescence model can be rather controlled if you are in a dilute system, and it's sort of the last kind of very weak interaction, right? That's, I think, what it was originally also designed for when you, coalesce nuclei into deuterons and things like that. But if you are in a strongly interacting environment, then it becomes a little bit different story, I would think, right? Because I mean, the common law sort of is that we are not far from thermal and chemical equilibrium in these collisions. And then I feel a little uneasy if anybody comes up with a description where you're relatively far away from that, right? And I don't know, I don't know what the different models have to say about it. I'm just saying I would be very much interested in what is really the chemistry, say the ratio, the inclusive ratios of the various hadrons in a given model, and what controls it, right? And then I mean that goes a little, and it may be doable, as Paul, for example, discussed, and you too, I guess, and so is that maybe there is a choice of parameters which is more preferred than others, right? But if we base the choice of parameters,
I fully agree, Ralph. Of course, it will be good to go into the formulas and clarify better how much you can change about the chemistry, what really controls it.
Right.
You can go everywhere, or there is some limit.
Right.
That I fully agree. I mean that at the end, it can be that you get something different from a statistical hadronization model. Still, we will see with the data. Of course, we have to get a better understanding of what is there. For example, we are okay. I agree that it's something to be done to understand better how the yields come out at the end and what drives them.
Yeah. Okay. Great. Yeah. That was basically what I tried to advocate, that we understand even inclusive chemistry, right? Then we can discuss how we distribute them in PT. But to begin with, do a Lorentz invariant quantity, which is just the total yields, right? And see how they are controlled by model parameters.
Yes, of course, I can tell something that you like a little bit less. It can be that really you go to very small momenta and is not that good. But when you are in the tail at 3, 4, up to 10 GeV, you get a good description, like it was for the original coalescence model in the light quarks. Or you get some futures that are interesting. That can also. I agree that one has to know what gives for the yields and what drives it. Absolutely.
Can I just make a little comment about the chemistry? For example, I observed that in the basic coalescence model, pretty much the only parameter that was dealing with the strange quark and the quantity of strange hadrons that you get is actually just the strange mass quark. That was the only thing. And for example, the density of strange quarks in the medium was not taken into account in any way. And I found pretty sad that it was like that.
Yeah, I share your concern. However, I would say that if the density, if it depends on strange quark mass, you might be able to make an argument that this is related to the thermal equilibrium abundance of the strange quarks, right? Or is that excluded?
Not sure.
Okay, thanks.
Well, the only thing I can share with you on this respect is that we observe that depending whether it's on the kind of really algorithmic approach, whether you make the coalescence in the fluid cell or if you make it in the lab, then of course this energy conservation problem induce some changes. But on the top, they are of the order of 10%. But okay, this is only one part of the problem. There are other issues.
No, I agree. I mean, clearly, if you have a frame dependence, the best you can do is work in the thermal rest frame and then boost it, right?
It's not clear because for the fragmentation, you do not do the fragmentation in the rest frame. I mean, once you decide
not fragmentation. Fragmentation is a phenological concept which is, of course, defined in the lab frame, really, right? Yes. I meant for the coalescence. I meant just for the coalescence.
Yeah, but somehow physics is an interpolation between both. Okay, I suggest that this is a really fascinating topic, but it seems there is less concrete ideas about how we should root this more deeply, and time is passing, and especially for friends from Asia. I don't know whether there's still some, but I think yes. Maybe we could close it here. And